All right, hey everybody, today we are going to start chapter 9, which is all about coordinate proofs. Um, so don't let the word proof scare you. We're not going back into the full heavy proofs that we're normally used to seeing. Coordinate proofs are just a way of using algebra to show that something is true. So if I want to show that segments are congruent, I can use this to show triangles are congruent by side, side, side. If I want to show a triangle is isosceles so that two of the side lengths are congruent, or that it's equilateral so all three sides are congruent. Anytime I'm trying to show two sides of something are the same length, we're going to use our distance formula. And a reminder, here's what our distance formula is, okay? If I want to show that segments bisect each other, or a point is in the midpoint, or any point bisects a segment, that's going to be our midpoint formula. Because if I'm bisecting a segment, the point on that segment is the midpoint. And the last thing we're going to look at is if we're trying to show that two segments or lines are perpendicular, we use our slope formula. So if I want to show that a triangle is a right triangle, I should have two sides that are perpendicular because they'll create that right angle. Or if I want to show a quadrilateral as a rectangle or a square, or that diagonals are perpendicular, all of those things we're going to use the slope formula. So none of these formulas that you see in front of you are new to us. We've done all of these so far this year. Now we're just going to use them in another way. So let's take a look. I'm given three vertices for a triangle, and I want to know whether or not the triangle is isosceles, scalene, or equilateral. So this is going to tell me that I'm going to be doing the distance formula. All right? Because I'm looking at the lengths of the sides. If all three sides are the same length, then it's going to be equilateral. If only two are, then it's isosceles. If none of them are the same, then it's scalene. Okay, so the first thing that we're going to do is we're going to start off by plotting the triangle. So we're going to go 4, 2 is point A. And then we're going to go -1, 4 is B. And then 2, -3 is C. And then we will connect our points here to make our triangle. All right, so I want to know, again, we're looking at lengths of sides. So we went ahead and did the first one for you here. So if I look at AB, right, I'm going to do, remember this is x1 minus x2 and y1 minus y2. And remember, it doesn't matter if you say 1 minus 2 or 2 minus 1. It's the same thing, okay? So we did -1 minus 4 quantity squared, and then 4 minus 2 quantity squared for AB. This gives us the square root of 29. I'm not super worried about simplifying anything right now, because even if it's not, and this does not simplify, but even if it did simplify, we could see here whether or not things were the same. Okay, so let's take a look at BC. So if I look at BC, I'm going to be looking here. So if we do x1 here, y1 here, x2 and y2, all right, we're going to do the square root of, I'm going to do -1 minus 2 quantity squared plus 4 minus a -3 quantity squared. And this is going to give me the square root. -1 minus 3 is -3 squared is 9. And 4 plus 3 is 7 squared is 49. So 49 plus 9 is going to give me the square root of 58. So right now these are different. So we know it's not going to be equilateral. All right, so then we're going to look at AC. And we'll just use this one as x1 and y1 here. Okay, and we're looking here and here. So again, it's going to be the square root. And then I'm going to do x1 minus x2. So I'm going to do 4 minus 2 quantity squared. And then we're going to do the y's. 2 minus a -3 quantity squared. Okay, 4 minus 2 is 2. 2 squared is 4. 2 plus 3 is 5. 5 squared is 25. So this is going to give us the square root of 29. So now I see that AB and AC are the same length. So that means that triangle ABC is going to be isosceles. All right, so this is our answer. But again, when we're doing a coordinate proof, then we are showing these steps. That's all that a coordinate proof is, would be showing your work, essentially, to show that something is true. All right? So let's take a look at another one. I want to know whether or not triangle ABC is a right triangle if I look at our points here. So again, we're going to start off by plotting our points. Point A is at -4 and then 6. B is at -1, 2. And C is at 3 and 5. And again, we're going to go ahead and connect those points. So we're looking to see whether or not ABC is a right triangle. So the big key of the right triangle is that I have a right angle, which means that two sides are perpendicular. All right? And in order to show that two sides are perpendicular, I'm going to use the slope formula. If I look at this triangle, I'm going to use this picture because they're giving us the coordinates so we know it's actually to scale. This is the only angle here that could possibly be a right angle. Whether it is or not, we'll find out, but we want to look and see. So that means that I'm going to do the slope of AB, and I'm going to do the slope of side BC, and we're going to compare those two to see how it is. So remember, our slope is y's first, so it's y2 minus y1 over x2 minus x1. So if we start with AB, okay, I'm just going to call this x1, y1, x2, y2. And again, guys, it doesn't matter if 1 is first or 2 is second, as long as you are consistent. All right, so we'll do it in this order. We'll start with y2, which is 2, minus y1, which is 6, over x2, which is -1, minus x1, which is a -4. So subtracting a negative means we're adding. So this is going to give me 2 minus 6 is -4. -1 plus 4 is a positive 3. So the slope of this is -4/3. All right, then we're going to look at BC, and I'm just going to leave B where it is, and we're going to change C to x1, y1. All right, and we're going to do y2, which is 2, minus y1, which is going to be 5, over x2, which is -1, minus x1, which is 3. So 2 minus 5 is going to give me -3. -1 minus 3 is going to give me -4. This is going to reduce. Negative over negative is a positive. So what we're going to look at is here and here, and notice that these two are opposite reciprocals. And if they are opposite reciprocals, that means that they are perpendicular slopes. So that means that triangle ABC is a right triangle. All right, but again, the whole point of this is showing why and showing those steps. Okay, that's the point of the coordinate proof, is you are showing where those numbers came from and showing the formula and all of that good stuff. All right, so if you have any questions on that, make sure you write that on your paper somewhere. And we're going to go ahead and do another example. So now we're going to look at quadrilaterals, okay? Remember, our types of quadrilaterals, we had trapezoids, parallelograms, rectangles, rhombuses, and squares. Okay, and if it's none of those, then it's just a quadrilateral. So these are the things that we're going to look at here. So again, just like we started before, we're going to start by graphing. So point A is at 0, 2. All right, B is at 3, 6. C is at 8, 6. 8, 6. And D is at 5, 2. All right, so we're going to connect our coordinates here. All right, so couple of things is you should automatically, when you see this, be starting to think about a parallelogram. I know that AD and BC are parallel. Okay, because they are both horizontal lines. And their slope is 0. Okay, so what we're going to look at is, are the other sides parallel as well? And then we're going to look and see, well, could this possibly be a rhombus? This is obviously not a rectangle, so we don't really have to worry about that. But we want to show whether or not it's a rhombus after we look at parallelogram. So what we're going to look at here is I'm going to find the slope of AB. All right, and I'm just going to do x2, y2, x1, y1. And remember, y's on top. So it's 2 minus 6 over 0 minus 3, which is going to be negative 4/3. Okay? Then we're going to look at the slope of CD. And with this one, same thing. We'll do x2, y2, x1, y1. Again, guys, it doesn't matter which one you choose to be 1 and which one you choose to be 2, as long as you are consistent. All right, so we're going to do y2, which is 6, minus y1, which is 2, over x2, which is 8, minus x1, which is 5. 6 minus 2 is 4. 8 minus 5 is 3. Oops, okay, so this is a negative 3 up here. So then we have 4/3 here. So they're both 4/3. Sorry, I missed that negative. Okay, so since both of our slopes are 4/3, I know that AB is parallel to CD. So now I know that I at least have a parallelogram. So then the next thing that I'm going to look at is, could this be a rhombus? Now, I can show that this is a rhombus in 2 different ways, and it depends on what way you like better. If you prefer to do slope, we can look at the diagonals, because remember that when we think about properties of our rhombus, I know that my diagonals are perpendicular. So I could do the slope of AC and the slope of BD and see whether or not the diagonals are perpendicular. I could also find the length of BC and the length of CD and determine whether or not those are congruent. So if you prefer distance formula, you can do it that way. If you prefer slope, you can use the diagonals. So those are things that we can use that are properties of our rhombus to help us figure out whether or not this shape is a rhombus. So since we already did slope over here, I'm going to go ahead and do distance, and it doesn't matter which pair of sides that you pick. You just have to do 2 sides that are next to each other, because since it's a parallelogram, remember, we already know that BC and AD are going to be the same. We know AB and CD are going to be the same. Well, so here's the nice thing. If I do these 2, let's just do AD. The length of AD, I don't need to do distance formula for, because it's horizontal. So it's 1, 2, 3, 4, 5. The length of AD is 5. Then we're going to do the length of DC, or I could do AB, whichever one I want. Okay, square root of And these are already labeled as D and C, so we're just going to leave it here. So x2 minus x1, so we're going to do 8 minus 5 quantity squared plus 6 minus 2 quantity squared. 8 minus 5 is 3, squared is 9. 6 minus 2 is 4, squared is 16. 9 plus 16 is 25, and the square root of 25 is 5. So since these are the same length, this is the same length as this, I know that I can say that ABCD is a rhombus. Okay, so remember, when we're showing these things, we need a parallelogram property and a rhombus property. My opposite sides being parallel is my parallelogram property, and my consecutive sides being congruent is going to show that my rhombus is there. Again, we could have done slope to show that AC and BD are perpendicular. Okay, and those two slopes should be opposite reciprocals of one another. All right. So let's do another one of those where we're looking at a quadrilateral again. And we are going to start by graphing. So point E is at 1, 5. F is at 7, 8. G is at 6, 4. And H is at 4, 3. And again, we're going to connect these points. So right away here, we should pretty clearly see that we're not looking at a parallelogram. So what I want to know is whether or not I can show that this is maybe a trapezoid. Because if it's not a parallelogram and it's not a trapezoid, then it's just a quadrilateral. So let's take a look. And to show that I have a trapezoid, remember, one pair of sides should be parallel. So we're going to find the slope of EF. And we're going to find the slope of GH. And see whether or not those are the same. All right. And I can see that these are very clearly not the same. And in a full proof, we would want to show that they're not the same. But for now, I'm okay if you just show what you know what is true. All right, so when we look at these two slopes, we're going to start with EF. So it's going to be y's on top, so 5 minus 8 over 1 minus 7. Okay, 5 minus 8 is going to give me negative 3. 1 minus 7 is negative 6. So I have a slope of 1/2. All right, if I look at GH, all right, same thing. We're going to do y's on top, so 4 minus 3 over 6 minus 4. 4 minus 3 is 1. 6 minus 4 is 2. I have a slope of 1/2. So I know that EF is parallel to GH. And I know that EH is not parallel to FG. So that tells us it's not a parallelogram. All right, we know at this point that we have a trapezoid. Now, the other thing that we want to look at is whether or not we have an isosceles trapezoid. So in order to check on that, we're going to do distance formula for those two sides to see whether or not they are the same. So we're going to start by finding the length of EH, and it is the square root of, okay, we're using E and H, so subtract your x's, so 1 minus 4. Quantity squared plus my y's, 5 minus 3, quantity squared. All right, so that's going to give me the square root of 1 minus 4 is negative 3, squared is 9. 5 minus 3 is 2, squared is 4. So this is going to give me the square root of 13. All right, then we're going to do FG. And find that length. So we're going to look here at these two. Again, we're going to start by subtracting our x's. So it's 7 minus 6, quantity squared, plus 8 minus 4, quantity squared. 7 minus 6 is 1, squared is 1. 8 minus 4 is 4, squared is 16. So this is the square root of 17. These are not equal. So then we can just say that EFGH is a trapezoid. We don't know what kind of trapezoid it is, or it's just that we know that it's not an isosceles trapezoid. So it's just a general trapezoid, okay? Not any of our special information. All right, again, if you have questions on that, please make sure that you are writing it down. All right, and we're going to look at one more example here. I'm given 4 coordinates, and I want to look at whether or not 2 triangles in there are congruent. So let's take a look. Start again, as usual, by graphing. K is at -2, 1. L is at -2, 3. M is at 1, 3. And P is at 1, 1. So then again, we're going to go ahead and connect these guys. So we've got a rectangle here, okay, because all of our sides are horizontal and vertical, so we know that. So then we're looking at KLM. So triangle KLM, we need this diagonal, and MPK is going to be this one. So I'm looking at whether or not this triangle over here is congruent to this triangle over here. So the first thing we're going to look at is to show triangles are congruent, we have a couple of ways that we can do that. We have side, 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 angle, side, angle, angle, side, angle, side, angle, and HL. Okay? So in order to show those, we're going to either use side, side, side. In this case, we could use side, angle, side, or HL, because I know that these are right angles, and I could show that the slope of horizontal and vertical lines are opposite reciprocals. Or the other way that we can do this is by doing side, side, side. So the nice thing about this one is that it is a rectangle, and my sides are horizontal and vertical. So I can start by saying, all right, I know that the length of LM is 1, 2, 3. Okay, I know the length of KP is 1, 2, 3. So I know that LM is congruent to KP. So there's one side. Okay, then we're going to look at KL. KL is 2. MP is 2. So I know that KL is congruent to MP. So there's another side. And then I know that KM is congruent to itself. So this one I didn't actually have to use much coordinate geometry because they were horizontal and vertical, and I'm okay with you counting those. So I know that KLM is congruent to triangle. So now KL is going to match up with MP. And then we have M and K are switched. So that's K. Okay? And this will be by side, side, side. And remember, it's congruent, so it's no similarity. Again, the other thing we could have done is I could have done the slope for these two sides and the slope for these two sides to show that they are perpendicular. So I get a right angle. And I could use side, angle, side for that. Or I could use H and then one of my L's. But I could do this using slope. All right. So just as a wrap up here, if we look at these distance formula, we're going to use distance formula to find the lengths of segments and to classify figures. All right, we're going to use the slope formula to determine two lines or segments are parallel or perpendicular. And we can use the midpoint formula to determine if we have a point that's bisecting something. So some of the other things that I could have used for that is done midpoint formula on the diagonals of the quadrilateral. So we could have come back here. Oh, too far. To this one. To see if it was a parallelogram, I could have done the midpoint of BD, and I could have done the midpoint of AC to see that they were the same, which would actually be right here. I know I didn't draw it very well. And if the midpoint is the same in both segments, then they bisect each other, which is our parallelogram property. So that could have given us parallelogram. All right? So if you have any questions, make sure you write that down and ask in class tomorrow. I hope you guys have a great night. We'll see you later.